All right, continuing with 9.1, sequences. Now, of course, not all sequences will have a limit, just like not all functions have a limit. And if the function, like that one I did earlier, where everything increased by 3 each time, or the one where everything decreased by -5 each time, neither one of those will converge. They diverge. And the way to say that the terms increase and continue to increase without bound is to say that this limit is infinity. And like where you're subtracting 5 as n approaches infinity, that sequence was headed towards negative infinity. And if you get infinity or negative infinity, that certainly means that the sequence terms are increasing without bound, so it does not converge, it diverges, or they're decreasing without bound, and that also means that they don't converge. So in both of these cases, we would say that the sequence diverges if either of those two things occur. All right, so theorem 9.2, the properties of limits of sequences. So if we're told that the limit as n approaches infinity for some a sub n sequence actually exists and is the number L, these are givens, and the limit as n approaches infinity of some other sequence b sub n, and it converges, we'll say that its limit is called k. The first property says that just like all limit properties that we saw when x was approaching something, those same properties are pretty much holding here. So these aren't really different from what you've seen before. It's just an acknowledgement that the properties of like the scalar multiple, you're multiplying by a constant c. So c is any real number. Forgot to say that. If you have a scalar multiple, some real number multiplied by your declaration a sub n of what the sequence formula is, that constant can be brought out in front. And of course, that's one of the reasons why we have that same property for integrals. So, because this property exists for limits. And for sigma, by the way. But that's another story. Another limit is if you had the sum of two different formulas, or the difference of two formulas, you can distribute that limit and do each of those terms individually and separately. So the limit sort of distributes over addition and subtraction. And of course, from our givens up above, by substitution, this is L and this is K. Number 3. If you have the limit of a product of two formulas, so a sub n multiplied by b sub n, that's going to also be something that you can separate and take the limit of a sub n and multiply it by the limit of b sub n. And by substitution, the first one is L, the second one is K, and so the answer is L times K. And then for a quotient, the same thing happens. So the limit of a quotient, we can take the limit of the numerator and divide that by the limit of the denominator. By substitution, that gives you L over k. Now notice in the book they left out the middle step for numbers 2, 3, and 4. So hopefully that helps you understand a little bit better how they arrived at those properties. Okay. Turn to the next page. All right. So one of the symbols that you need to know, and I hope you encountered it before today, because it's a really handy symbol, and in pre-calculus I end up using it quite a bit, and it's called n factorial. And what that means is that, and they write it differently from how I do, which is fine, but when I do like 5 factorial, that means write the product of all of the positive integers through 5, up through 5. So what I do is I start at the top and go down. 5 times 4 times 3 times 2 times 1. They go up 2, so they start at 1 and multiply all the numbers, positive integers, until you get to the number n. Either way is fine. They're equivalent, so it doesn't matter which way you write it. So 1 factorial, there's nothing to multiply it by, it's just the first number. So 1 factorial is 1. Kind of seems like a special case. And then for some of the counting procedures that you do, like in statistics and probability and advanced pre-calculus, like I'm thinking specifically of the binomial theorem, you have to have a value for 0 factorial for the formulas to work out right. And so this one is defined as 1. That triple equal sign means we're defining it to be that number so that things work out nicely. It does not follow the definition above. It does not do that. There's no such thing as using the rule above when it's 0. You do need to be careful. The order of operations, it's kind of like exponentiation. If you have 2n factorial, the factorial, like an exponent, is more important than the multiplication. So this is going to be 2 times whatever n factorial is. Okay? So that's going to be doubling the product from n times, next one down is n minus 1, next one down is n minus 2, times dot dot dot, times 3 times 2 times 1. Okay? Now, if you want to interrupt that order of operations and put 2n inside of parentheses, this is going to be, I'm going to write it in their way, 1 times 2 times 3 times dot 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 times n times the next one, n plus 1, times dot 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 until you get up to times 2n. Let's do a simple example. Let's do 2 times 3 factorial and 2 times 3 factorial. So 2 times 3 factorial is 2 times 3 times 2 times 1, which is 12. Because of the parentheses, we're going to do that multiplication first. 2 times 3 is 6. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which, if I remember correctly, is 2, 6, 24. Nope, I can't do that in my head right now for some reason. 24 times 5, 720 times 6 is 720. Well, I guess I can. By the way, there is a way on a TI-84 and a TI-83 to access that command. So if you're in your home screen of a TI-83 or 84, you're going to type your number like 6 in your home screen, so type that. And then you're going to access the factorial by hitting Math, that math button. Oops, excuse me. Then go over to probability, which is one of the submenus, PRB. Oops, that's a capital R. PRB, at least on my calculator is. Go to PRB, and it's the fourth option down. Choose that fourth option. You'll see your number and the factorial sign behind it. And then when you hit enter, it does the calculation. So you won't have to do all that in your head. There's a way to make it in your calculator a lot faster than typing 6 times 5 times 4 times 3 times 2 times 1, for sure. So that's a good thing to know, how to get to that factorial button. Kind of handy. Okay. So another theorem that's really useful is the Squeeze Theorem. Let's say that we know all about a sub n, and we know what its limit is, and it's L. And we have another one that we know all about as well. It's easy. It's a super duper easy one to find out. Both of these are easy, let's say. And it's also L. If for every n, every positive integer, it's true that a sub n always gives you answers that are smaller than or equal to a new sequence that we're trying to find out about, C sub n is really hard, difficult. Oh my gosh, I can never get this one. It's just not working out. Well, that's why we're going to sandwich it between two other functions that are reasonable. So C sub n in turn is less than or equal to all of the terms of B sub n. And we don't know how to find the limit for C sub n directly, but because C sub n is sandwiched between A sub n and B sub n, if as n goes to infinity, A sub n heads toward L, and as n approaches infinity, B sub n also approaches L, that means that C sub n must also approach L. And again, A sub n and B sub n are well behaved, nice, easy to figure out limits. C sub n is between them. We don't know how to do it, but we can sandwich it between two known ones. If they both go to the same number L, then the one sandwiched between them is forced to go to L as well. Okay, I'm going to use that to show you a limit that you might not know how to do. And we're going to sandwich it between two things. So we're using this Squeeze theorem. Some people call it the sandwich theorem. You've heard me say that now a couple of times, sandwich between. It's also called that, sandwich theorem. And that'll slip out because I've heard that a lot. I've heard Squeeze theorem a lot as well. So I use them interchangeably. So we're going to have powers of -1 times the fraction 1 over n factorial. All right. So first of all, let's start this, and you're not going to understand exactly why I'm doing this quite yet. Hopefully it will become clearer as we go. So let's talk about what n factorial is. It, of course, is 1 times 2 times 3 times 4 times 5 times 6 times ... times n. And if you think about it, how many terms are there? Well, how many factors are there? Well, there are n factors. So if we stopped at 3, 1, 2, and 3, there'd be 3 factors. So n is the number of factors. If we were to take away the first, say, 4 of these and simplify that part of it, 1 times 2 times 3 times 4 is 24, times the rest of those numbers. how many factors are there being multiplied together now, ignoring the 24 for just a moment? Well, we've taken away 4 of them to write the 24, so right here there are n minus 4 factors in that product. I know this sounds like a hocus pocus, but it actually does work. Now I'm going to take something that will seem completely random. The n factorial made sense because it's part of my problem up there. So thinking about n factorial doesn't bother me, but why did I think of 2 to the n? Well, you're not going to have to produce this argument for me, so just go with the flow a little bit here. 2 to the nth means, of course, that we're multiplying 2 times 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 2, etc. We're only multiplying by 2's. And if it's 2 to the nth, how many factors are we multiplying? How many 2's are we multiplying together? Well, there are n of them. Like if it were 2 cubed, that's 2 times 2 times 2. There are 3 of them. 3 of the 2's in that case. So there would be 3 factors, 2 and 2 and 2. So if we're doing 2 to the nth, that's n factors. I'm again going to split off the first 4 and find that product. 2 times 2 times 2 times 2 is 16. I probably should have underlined over here. That's where we got the 24, and that's where we got the 16. And then we're multiplying that 16 by the rest of the 2's. Well, how many are there for the rest of the 2's? Well, we took out the first 4, so there are n minus 4 factors left. Oops. Now, one thing I'd like for you to look at here is, do you agree with me that by the time we get to at least 4, if we stop with n being 4, do you agree that 24 is bigger than 16? N factorial is bigger than 2 to the nth as long as we're beyond 4 or equal to 4. Let me just start with that. Where n is equal to 4, n factorial 24 would be bigger than 2 to the nth. I'm sorry, we're talking about equals. It's going to end up being greater than or equal to in a second. I keep saying it as greater than first. But all I've established first is that 24 is bigger than 16. So actually, it is greater than, not or equal to. I'm just going to go ahead and say it's true that it's definitely greater than or equal to. That's not a false statement. So we're going to leave the greater than or equal to in there. Hold on. Yeah, and the reason I want to do that, make sure I've set this up correctly up at the top. Hold on. Oh, yeah, that's fine. It's because the squeeze theorem uses the or equal to notation. So if you can add or equal to without saying something false, feel free to add the or equal to so that it matches the squeeze theorem declaration. Okay. So you agree that that's true. So this is where I was going to say when n is equal to 4, I'm going to write just the bottom part of that equal sign because it is going to end up being true for greater than or equal to. That's where I was going with that or equal to. Anyway, that's the or equal to part of it. And let me go back up here. Now, do you agree that if I multiplied 5 times 6 times 7, that's bigger than 2 times 2 times 2? So the n factorial, all of those factors are all bigger than 2, and they're the same number of them. So if you multiply n minus 4 numbers times each other, or times each other, I guess, and those numbers are only getting bigger, 5 and 6 and 7 and 8, 9 and 10, that's going to be bigger than the multiplication of a bunch of 2's, the same number of 2's. So 5 times 6 is bigger than 2 times 2. 5 times 6 times 7 is bigger than 2 times 2 times 2. So we can say that as long as n is greater than or equal to 4, n factorial is greater than or equal to 2 to the nth. Okay. So now let's see what I want to do next. let's say that we write that inequality for n greater than or equal to 4. I'm not going to keep writing n greater than or equal to 4. Just keep that in mind. That's true for the rest of this problem. I can write that inequality if I want to in reverse order, so that 2 to the nth is always less than or equal to n factorial. Okay. And then I want to take the reciprocal of both sides of this inequality. So I'm going to take the reciprocal of 2 to the nth, and I'm going to take the reciprocal of n factorial. And of course, what I'm moving toward now is our a sub n that we started with. So I'm trying to get that in there. Now, if I have something that's true like 8 is smaller than 23, if I take the reciprocal of both sides, how does 1/8 compare to 1/23? You can put that in your calculator if you want to. You could have used 8 and 100. So how does 1/8 compare to 1/100th? Well, that changes the direction of the inequality. When you take the reciprocal of both sides of an inequality, it switches direction. Oops, made a stray mark there I didn't mean to make. Okay. So then, as a side issue, what if I were to multiply both sides of that inequality by -1? Well, if I did that, I'd have the opposite of 1/2 to the nth and the opposite of 1/n factorial. And when you multiply both sides of an inequality by -1, that changes the direction of the inequality, so greater than becomes less than or equal to. And then I want to switch the order in which that's written. So I want the n thing on the left side of that inequality, so that'll be greater than or equal to -1/2 to the nth. Now, if you raise -1 to a power, an integer power, when n is odd, your answer will be -1. If it's even, however, -1 squared, for example, or -1 to the 4th, the answer will be +1. So, since we're only using positive integers, all positive integers are either even or odd. The answer is either -1 or 1. And we have to allow for both possibilities. So, what that implies is that this 1/n factorial, in this case, that's -1 to the nth, where n is even, where you get a +1 times that. So this is a true statement when n is even. And I could rewrite this as -1 to the nth. When n is odd. Now, if I want to consider both of those cases at the same time, actually, I didn't really want to switch the direction of those. I'm so sorry. I'm going to switch them back. My apologies. I shouldn't have done what I did earlier. So I'm going to rewrite it this way, with the 2 to the nth in the denominator on the left side of this one when n is odd. So I guess this is a conclusion that we can come to. When n is odd, that's true. And I also want to reverse this one. So I'm going to have the 1/n factorial expression on the left side. And there's a property of inequalities. Transitivity is the name of the property that says that if A is less than B and B is less than C, the transitive property of inequalities says that that means that A has to be less than B and B has to be less than C. Okay, so sorry, that's not transitivity. It's just a definition of the compound inequality. I called it by the wrong name. Wrong name. Sorry about that. So if you look at our two expressions, what we can say is that if you look at this one as A less than B, A is less than B, so that's A, is less than or equal to B. And then we look at the second one, and our B is less than or equal to C, and our C here is 1 over 2 to the nth. Okay, so I've established that the sequence that we're trying to find a limit for can be sandwiched between these two functions. And my claim is that I can find the limit of those without a lot of problem. If I have a constant like -1 over a power of 2, where that power is an increasing exponent, you're going to get a larger and larger denominator underneath the constant, and that will head towards 0. And I can find a limit for the other function that our problem is sandwiched between, is the one on the right, and that one, by the same reasoning, is also headed towards 0. So by the squeeze theorem, we can claim, because we've set up the fact that our function, or our expression of our sequence, is always trapped between those two, where A is -1 over 2 to the nth and B is 1 over 2 to the nth. We can therefore claim that because ours is sandwiched between those two, that the limit as n approaches infinity for what we've sandwiched in between has to go toward the same value as the two between which it's sandwiched, and so that has to be 0. So there's an example of this squeeze theorem, sometimes called the sandwich theorem. And so if you looked at a graph of these sequences, let's make this one way up here, and let's make -1 down here. So 1, 2, 3, 4, 5, 6 ought to be sufficient. So let's look at first graphing a sub n equals 1 over, sorry, let's make a -1 over 2 to the nth. I'm trying to be consistent with what I said earlier, is why I paused. Okay, so when n is 1, that'll be -1/2. When n is 2, that'll be -1/4. When n is 3, that'll be -1/8, -1/16, -1/32, -1/64. Okay, then let's make b sub n be 1 over 2 to the nth. So when n is 1, you get 1/2. Then a 4th, and an 8th, and a 16th, and a 1/32, and a 1/64. Okay. And then if we were then to graph c sub n, which is -1 to the nth times 1 over n factorial. When n is 1, -1 to the first is negative, so that'll be a negative answer. And 1 over 1 factorial is 1, so -1 is that answer. Notice it's not between a sub n and b sub n. It's beyond them at that stage. 2, -1 squared is +1. 1 over 2 factorial is 1 over 2. So that's a half, which is actually about right there. So still, that red dot's not between the green and aqua. So we're still not between those two. For 3, -1 cubed is negative, so that'll be a negative answer. 1 over 3 factorial is -1 sixth, which is just a little bit outside. And when we get to 4, -1 to the fourth is 1. 1 over 4 factorial is 1/24. This was 1/2, 1/4, 1/8, 1/16. So we're now inside. And for the rest of those answers, if we actually calculated them, all red answers are now between the green and the blue. So by the time we get to n equals 4, our red dot is closer to the n-axis than either of those two, the green dot or the teal dot, or whatever, aqua dot, whatever color that is. So because the blue heads, the aqua heads towards 0 and the green heads towards 0, red, which is between those two after n is 4, or equal to 4, then we start being able to say that C sub n has to head toward 0 as well. Hopefully that graph helps you understand more about what's going on and you're able to visualize it. Okay, the next theorem is a really important one, the absolute value theorem. So make sure that you know this one because it'll come into play later. If we find the limit as n approaches infinity of the absolute value of a sequence, so in other words, any positive terms will stay positive, 0 will stay 0, and negative terms will turn into their opposites. If that limit as n approaches infinity is 0, it's only when it's 0, okay? It's only when it's 0, so it's really important that you realize that that's true, but only when it's equal to 0, then we can claim for sure that the limit of the non-absolute value version, just a sub n, it will have to go to 0 as well. That's kind of a nice little theorem to have in your back pocket. Okay, this looks like a great place to pause, so I will go to the next video.